So welcome back to the last class this week. I'm just going to quickly do a little review of what we talked about yesterday. I have a couple things to mention, and then we'll get into the next section, which I think is one of the last sections, 4.4 of chapter 4. So if you were here yesterday, you would remember me talking about solutions. Solutions are homogeneous mixtures of more than one chemical that look like one substance. So the easiest example I gave yesterday was salt water, NaCl plus H2O. It still just looks like water. Um, you guys have made homogeneous solutions, I'm sure, before. If you add sugar to milk or not milk, if you add sugar to tea or coffee, it basically makes a homogeneous solution. There's an exception if you're using like loose tea, but the idea is if you add sugar to hot water, it dissolves and it looks like a solution. Now, depending on how much sugar you add, we would call that the solute. You can create three types of solutions. So I did this yesterday. I'm not going to go over this again, but we talked about unsaturated. This has some solute. Remember the term solute? That's what gets dissolved in your solvent. Typically, the solute in chemistry 1120 is typically something like ionic compound, maybe something like sugar. The solvent in chemistry 1120 is typically water. Now, any of my chemical engineering students, when you get to hydrocarbon chemistry, there's other solvents that are used in industry like toluene or xylene. These are much different than water, but for chemistry 1120, the solute is something like sugar or salt, and the solvent is water. So an unsaturated solution has some solute in it. A saturated solution has the maximum solute dissolved in it. This depends on temperature, but it's, in theory, the maximum amount of solute. And a supersaturated solution, this is an exception. This is special. It's rare and it needs special conditions, but this is when you have extra solute. I mentioned the other day what this means. In order to get extra solute, you typically need to modify the experiment. You need to heat up the water, add extra solute, then cool it down. So these are three different types of solutions. And I'm going to show you a cool video in a minute, but let me kind of get to the new part of today, and I'll show you a really cool video. I just got a private message in the chat about some questions for the lab number 7. So if you guys have any questions about your lab, save them for after class. And so yeah, and we'll talk about lab 7 after class if you guys have any questions. All right. Okay. So kind of hold on to that for till after. Okay. So a supersaturated solution. A really interesting thing happens with a supersaturated solution when you add extra solute, and it's called a seed crystal. And I'm going to explain this with a video in a minute, so it will make sense. If you have a supersaturated solution and you add what's called a seed crystal, it means extra solute. Because the supersaturated solution is so, unstable, when you add a seed crystal, you can see it on the top of that image there, it crystallizes, or precipitates is the proper word. It turns into a solid to become more stable. The whole reason I'm telling you this is because with a seed crystal, you can actually do a really quick experiment to tell which type of solution you have. So let me explain. A seed crystal is a small amount of solute that is added to a solution. If you are unsure of what type of solution you have, you can add a little extra solute. And again, that's all that I mean by seed crystal. It's a little extra solute. Now, this is what's interesting. If your solution is unsaturated, saturated, or supersaturated, three different things will happen. Okay, so what happens if you add a little bit of solute to an unsaturated solution? Well, an unsaturated solution can take more. So if you add a little seed crystal to this, it will dissolve normally, just like when you add sugar or something to tea or coffee. Okay, so what if you take a little bit of extra solute, a seed crystal, and you add it to a saturated solution? Remember, a saturated solution cannot take any more solute under normal conditions. So you add a seed crystal to saturated solution, it just floats or sinks to the bottom of the beaker. It will not dissolve. Okay, so again, keep this in your mind because this could be a good question for your test or final exam. I might say, what happens if you add a seed crystal to this type of solution? So unsaturated, the seed crystal dissolves. Saturated, the seed crystal will not dissolve. Super saturated is amazing. You guys are actually going to do this in an experiment later this year. So you will see this in the lab, but a super saturated solution causes crystallization or precipitation. It almost looks like it freezes. Solid forms here. And it's really, I'm not giving this justice. Like, you really need to see this. It's amazing. It's one of my favorite kind of physical reactions. It's not really a chemical reaction. It's physical because it's just a phase change. So give me a second here. I'm going to open up YouTube, my favoriteest thing in the world, and I'm going to show you the video. Okay. Okay, I'm going to share my screen. I hope this works. It worked this morning pretty well. If you're having a hard time seeing the video, you can do this on your own time. Just go to YouTube and I'll show you what to type in. Speaking of YouTube, this is my chemistry channel, and in my playlists, I have all of your videos uploaded. So you guys would be here in Chemistry 1120. And these are all the lectures I have uploaded, and I will send you that link again after this class. So, all right, anyways, let's go find this thing. So super saturated solution experiment. Now, this one's my favorite one here by this guy, Jeremy Krog. He only has about 2,000 views, so we'll add to that. And I'm going to skip ahead. Oops, okay. Right here. All right, so let me just go back. I hope you guys can see my screen, my YouTube. I'll make it full screen here. So in the YouTube video, we have a beaker full of a super saturated solution. You can tell that this solution has been heated up, but it also has been cooled down. I know it's been heated because I can see condensation up at the top. So what this guy did is he heated up a solution of water. Well, no, I guess, sorry, he heated up water. Then he added a lot of sodium acetate, like way more than you should have. And then he cooled it down. So this chemical now would be cool. It's very unstable. But as long as you don't mess with it, it's going to stay like this. So watch what happens when he adds a seed crystal. And again, all a seed crystal is extra solute. So he's just adding a little bit extra sodium acetate. This is a safe chemical. He's not wearing gloves, but it's fine. This is a chemical you make if you mix baking soda and vinegar, you would get this chemical. So it's pretty safe. Okay, so watch this. I love this. Oops. All right, so he's going to drop the crystal in, and it's going to happen really quick. So just pay attention. Oh, sorry. All right, do you see that? Do you see how cool that is? So, like to the untrained eye, to the average Joe, and none of us are average Joes anymore. We've learned a lot of chemistry. To the average person, you might say, "Oh my gosh, it's freezing. It's turning into ice right away." But it's not freezing. This actually would be a very hot reaction. If you touch the beaker with your hands, it would be very, very warm. So it's not freezing. What's happening is all the extra solid in that beaker is precipitating. It has so much solute that it's precipitating out as a solvent, or as a solid, sorry. All right, I'm going to show you one more thing because this gets even cooler. What if instead of dropping a crystal into the solution, what if we put the crystal on a piece of glass and we pour the solution onto it? This is one of my favorite chemistry demonstrations. Like if I was going to, go to a high school and show them cool chemical reactions, I would show them this one. So watch this. This is, I love this one. So, okay, again, what he's doing is he's going to pour the supersaturated solution very carefully onto that seed crystal. All right, so check this out. This one's even cooler. This reaction takes, like, he goes very slow, so I won't show you the whole thing. But it instantly precipitates. It turns solid. Right? I mean, it basically looks like magic. And I mean, it's not, it's science, but like if you showed this to a small child or someone who doesn't know chemistry, it would, it's kind of impressive. Just hold on for 1 second here. The old dog is going crazy. But you just check that reaction out. It's really cool. The guy goes so big with it, it tips over, which I'll kind of skip to here. I've never made one this high. Yeah, there we go. Boop, falls over. So pretty cool. I don't know. I think that's cool. I don't know if you guys think it's cool, but I like it.
Sir,
Yeah. Question?
the liquid,
Yes.
if it didn't touches any solute, it remains liquid, yes? If you stir it, you drop it.
That's a really good question. Okay. How do I answer that? The question was, if you guys didn't hear, if you didn't touch that to solute, like if we didn't add a seed crystal, would it stay clear and colorless? It depends. And I know that's not a very good answer, but you could make this happen if you shook it up really well. So we will do this in lab 8. And I've actually messed this up in front of like 30 students before, because as I was carrying the beaker, right? So the beaker, clear and colorless, beautiful solution. As I'm carrying it, I bump it on something, like I might hit it on the lab desk or kind of bump into a student or something. Instantly it crystallizes or turns into solid. So to answer your question, if you're careful, you can move this around, you can stir it, but if you suddenly bump it or drop something into it or tip it over even, it would probably turn into a solid. So yeah, to answer your question, if you're careful, it will stay liquid, but if you do anything aggressive, because it's so unstable, it will turn solid. All right, good question. And I'm going to leave it there. I mean, this you could go to YouTube tonight if you're bored and like look at so much of this, so many of these reactions. Like again, if I search for this again, there's so many of them, right? There's people in their kitchens, there's people in the lab. I mean, hundreds of these things, right? So anyways, I'll leave that for you guys and I'll move in to the next topic. All right, sorry, I'm gonna have to go back to the boring stuff now. All right, well, I guess, actually, speaking of the boring stuff, the other class didn't get very far today. just they whatever happened, they had a lot of questions and stuff. So I don't have much to explain to you today. I'm going to explain the factors that affect solubility, and then I'll kind of stop here. So we really only maybe 10 or 15 more minutes, and we're free for today. And if any of you have lab questions after class, you can ask me then. So just give me 10, maybe 15 minutes, and that's it. All right, section 4.4, factors affecting solubility. So we're going to go through all of these objectives. I will give you a hint here, wink, wink. The most important objective is the last objective, which we probably won't get to until Monday's class, which is not really a big deal. We're still doing okay for time. Okay. So as I mentioned earlier, solubility is the maximum amount of solute that can dissolve in a solvent, but at a specific temperature. Solubility definitely depends on temperature. And I mentioned this in class yesterday. If you want to try this, you can go to your kitchen now, get cold water, get hot water, and try to dissolve a tablespoon of sugar or salt. It will happen faster in the hot water. And I'll kind of explain how or why that happens. So there are 3 factors that affect solubility of a solid, liquid, or gas. The first factor is temperature. The second factor is pressure. And the third factor is the most interesting factor. And this factor is so simple that it can be confusing. The nature of the solute and the nature of the solvent. Now, what I'm saying here is, do they even mix? Like, or does it even dissolve? I'll give you an example. If I'm trying to mix sand from the beach, or sand from Doha, from the desert, with water, it's just not going to dissolve. It doesn't dissolve. Plastic beads don't dissolve. Your clothing doesn't dissolve in water. Rubber, I mean, so many different chemicals do not dissolve in water. So the nature of the solute, you just ask yourself, does it dissolve? Oops. Right? I mean, so that's a really weird one, but it is such an important factor. You can change the temperature and pressure all you want. But if the chemical isn't soluble, if the chemical doesn't dissolve, it's not going to dissolve. That's just science. It's how it works. So, like I said, the best example I can give is sand and water. It's just not going to dissolve. It's not soluble. So there's nothing you can really do. It won't work. Okay. So basically all I want to do today is show you temperature and pressure, and that's it. All right, temperature. Now this can be confusing because I'm going to give you 2 statements here, and the statements are opposite, and you'll see in a second. As temperature increases, solubility of a solid increases. So as you increase temperature, solids will dissolve more easily in a liquid. It says you saw this in a lab. Arguably, you saw this in lab 4, but you'll also see this again in lab 8. So that's pretty common sense. Well, maybe not common sense, but it's pretty easy to understand. Solids will dissolve easier in hot liquids. Now, this is where it gets a little bit, not confusing, but you need to be careful. Gases are the opposite property. As temperature increases in a solution, the solubility of gases decrease. That's why I'm a huge fan of carbonated drinks. Now, when I say carbonated, I mean like sparkling water, Pepsi, Coke, 7-Up, whatever. A carbonated drink is full of dissolved gas. The reason that Pepsi or Coca-Cola are so fizzy, they burn, they tingle on your tongue and your throat, it's because they have dissolved carbon dioxide in them. CO2. Okay, so that, yeah, if you've ever wondered why is Pepsi or Coke, why do they have bubbles in them? Why are they fizzy? It's because the people who make them pump carbon dioxide gas into them. Okay, so how can I explain this? As temperature increases, the solubility of the gases get less. It's the opposite of the solid. So just imagine you have two glasses in front of you of water, and on in one we have hot, I'll say cold H2O, and in the other we'll have hot H2O. And in that water, I have CO2 molecules just dissolved in that water. Okay, so I have cold water and hot water. They both have CO2 in them. Okay, so remember that temperature is a measure of kinetic energy, so the speed of the particles. So in cold water, the particles are slow. The gas molecules just move around very slowly. So like again, if I mentioned like Pepsi or Coke, if you drink a really cold Pepsi, it burns. You can feel the carbonation in it. Whereas like something like hot or warm Pepsi, it just doesn't taste as good. It's not as fizzy. Because in the hot drink, you're giving enough kinetic energy to the gases to escape. So, if you really want to keep a Pepsi or Coke carbonated, it's a lot better to put it in the refrigerator. It slows the gas molecules down. It keeps them in the drink. So that is a little confusing when you think about solids. So just make sure you know the difference. When temperature increases, solids become more soluble. When temperature increases, gases become less soluble. All right, last part of today, pressure. Now, pressure does not affect solids or liquids. We learned that, I think, in chapter 1. Solids and liquids are not compressible. Changes in pressure will not affect solids or liquids. Pressure only affects gases. And I can again talk about like Pepsi or Coke and gas and dissolved gases with pressure. But first, let's look at these diagrams. Here I have two beakers, and I have on top of them what's called a piston, or like a disc that I can push down to increase pressure. If you can't remember what pressure is, it's the force on an object. Okay, so when you put pressure on something, you're squeezing it or pushing it. So just imagine, look at the left, I have beaker A, look at the right, I have beaker B. In beaker B, I'm pushing down on the gas. I'm compressing the gas. And by doing that, I'm forcing, literally pushing all of those molecules into the water. And I know like it's hard to imagine chemistry or chemicals as like objects. It's so obscure. They're so small. You can't even see them. But really what's happening is when you push on a gas above a liquid, you're taking all of those gas molecules and forcing them into the liquid. So how do we relate that to real life? Now I prefer, like, I'm not a big fan of fountain drinks. I prefer drinks like in a aluminum can or a glass bottle. So if any of you, and I'm going to assume it's all of you, if you've ever opened a can of Pepsi, a can of 7-Up, Coke, whatever, you hear that distinctive sound, that hiss, that tst, that sound it's my favorite sound, I think, when you open a can of Pepsi or Coke, it makes that hissing sound. Well, what happens is when they make a can of cola or carbonated drink, they are doing that under immense pressure. So if you ever, like next time you pick up a can of Pepsi or Coke, just gently shake it. Don't shake it too much. You'll know what happens there. But just kind of shake it by your ear. you can hear the liquid in that moving around. There is gas in the can of Pepsi or Coke, a little bit of room in there. So what happens is that when the people are making your carbonated beverages, they're putting the liquid in, they're filling it with a bit of carbon or a lot of carbon dioxide, and then they completely seal it off from the atmosphere. They do this under pressure. So when you open up that can of Pepsi or Coke, that hissing sound is all of the gas escaping, not all, but a lot of the gas escaping because it's under so much pressure and that pressure has been released. So the minute you open up a Coke or Pepsi, that sound is the pressure being released and all of those CO2 molecules that were forced in the solution can now escape. They're like, we're free, we've opened up the gates, we're free, and they run away. So as pressure increases, the solubility of a gas increases. And again, that's because we're pushing it, we're forcing it into that liquid. So when pressure increases on a solid or liquid, no effect. These guys, as we learned in chapter 1, are not compressible. Can't squish them. They'll break before they get squished like a gas. All right, that's it for me today. Now, you guys, I don't know how or why, but I'm always faster with you guys. We do have time to get into this, but I'm going to leave it because the other class hasn't done this. So we'll save this for tomorrow. I say tomorrow, I mean Monday. But make sure if you're not here on Monday, you watch the recording. This solubility chart is in your data booklet, and we're going to learn how to use it not tomorrow, Monday. So that's it for me. If you guys want to go, you're free to go. Have a great weekend. But there was a question about the lab, so I'll answer that now. I'll just hit stop record. So again, if you guys want to take off and enjoy your weekend, have fun, wear a mask, be safe. But I'm going to answer some questions about the lab now. All right. Goodbye.